Okay, so we are recording, and the bell has started. The bell is actually a little bit.
Oh wait,
it's actually on time.
Let me just. Can I just quickly turn in my assignment? I just realized I forgot to. Because I was working until I had to leave.
Okay. Well, I was actually about to talk about the practice midterm because I just realized that we are already in week 12. I didn't know that until I was reminded, because after all, finals start next month, about a month away. So we only have 4 weeks left, thereabout. Yep. Yep. We are more than 2/3 done with this class, with all your classes, with the semester as a whole. So let's go ahead and I'll talk about the homework assignment when we get to it, so that will give some people a little bit more time to turn it in. If it's off by a few minutes, it's not a problem. If it's off by more than a few minutes, it is a problem. Okay, so we want to go to the practice exam, which is under recursion, because that's going to be the last topic of the current exam 2. Okay, so none of the graph stuff is going to be in the second exam, only up to recursion and the master theorem. So that stuff is going to be in the second exam. It's not going to be, I cannot promise that it is, it doesn't contain material prior to the first exam, because a lot of stuff it built upon itself. So the set theory stuff, it's unavoidable, okay? Because a lot of stuff built upon set theory. But the focus is going to be the material after the first exam and up to and including recursive subroutines and also the master theorem.
We did jump around a little bit.
We did jump around.
Going through exactly which of the topics we're going to be doing.
Okay, so let's go ahead and go through the topics. Okay, that's a good idea. So we did jump around a little bit, and the first exam included everything up to propositional logic. So in the second exam, we'll start with predicate logic. So we'll just kind of go through all the topics a little bit as an overview, and then we'll go to the exam from this spring as a practice. Okay. So with predicate logic, we talked about why do we need predicate logic when we already have propositional logic, and the main reason has to do with quantifiers. Okay, the existential quantifier as well as the universal quantifier. There exist is existential, and then universal is for all. Okay, so those things are missing entirely in propositional logic. We talked about Prolog a little bit because Prolog is the engine, is the implementation of predicate logic. We also talked about, I cannot remember which slide. It maybe it's not this particular one. Probably it's the next one. Okay, we talked about substitution. So that's a kind of important topic, is substitution, because that is not needed in propositional logic because there are no quantifiers, there are no variables, and then you have to instantiate, or you can bind variables to actual values. So the substitution part is actually kind of important. The only real theory behind substitution, or the only important definition, is what is a unification, and also what is a most general unification. So we briefly talked about this stuff here. I gave a few examples in class about how we can unify chunks of code and turn those into a subroutine. So we kind of talked about that a little bit. So we can go back to here and talk a little bit more about unification and most general unification in this case. Okay. So, but as an overview, I'm just going to move on and talk about the other topics that we also went over. How Prolog works is not going to be that important in this exam, in exam 2. I'm not going to test you guys on how Prolog works. Okay, that is just not in the scope of the curriculum of this class. Okay, but the predicate logic itself is important. So after that, we jumped around. We talked about some proof techniques already. Okay, I kind of sprinkled the proof techniques, kind of all over the place a little bit. We talked about proof by contradiction. Okay, I don't think did we spend any time on myth busting implication? Okay, so I can go over that a little bit. what that slide talks about is basically stuff that does not work. All the myths, you know, that is there are common misunderstandings. Okay, so we can go back and talk about that one. More proof techniques. Now this is where things, you know, get sprinkled around a little bit. Direct proof is something that we do kind of like, you know, by default, which is just going forward. Proof by counter example is just showing a particular case where the theorem does not work. Okay, so you only need one counter example to show something is not true. But proof by contradiction is the big one. Okay, where you have it's a two-step process. The first step is to negate the theorem, the very same theorem that you want to prove true, instead you negate it. After you negate the theorem, but you keep all the assumptions, then you prove that it is not possible. Okay, so that's proof by contradiction. Are there any questions about that one? So as I go over these general topics, if you have any questions, you know, we can kind of at least, you know, put it on a little document so I can get back to talk about those items. We also talked about induction. Even though induction has its own section, there's no content inside induction because I don't feel like talking about induction in vacuum. Okay, so instead of talking about induction in vacuum, we actually introduced proof by induction when we talked about probabilities. When we talk about the binomial distribution, that's when we actually talk about it. We did jump around a little bit. We talked about probability. We talked about combination, permutation. Not sure, did we get to frequencies and probabilities? I think that's, we may not have gone through this slide here. We did talk about when and how to use combination versus permutation. Okay. Yeah, the two homework assignments, you know, well, particularly the second one, you know, talks about, you know, how to use permutation in that case. So when do you turn it into combination? Okay, let's go back to this homework assignment and say, okay, how am I going to change the rules, or how do I change the assumptions so that instead of using permutation, you would have to use combination? Okay, so let me just kind of read from the beginning, and you guys can stop me and go like, ha, it's right there. Okay, you change this assumption, and then we have combination instead of permutation. The Lee family goes on vacation, family vacations 5 times per year. Okay, that by itself has nothing to do with either you should use permutation, combination, or none of those two. Okay, these 5 vacations are at specific times of the year. Okay, so this is starting to be important, okay, because now we are saying, okay, these 5 vacations are at specific times. Now this is the part where you have to pay attention, because it helps you decide whether, if we have to use either combination or permutation, this is the clue of which one we should use. Because it says right here, cost of airfare, hotels, and other vacation expenses, basically a bunch of items, okay, are sensitive to the time of the year. In this particular context, when something is sensitive to the time of the year, it also means it is specific, or it changes depending on which time slot you use for that vacation. In other words, ordering is important, okay? So when ordering is important, you use permutation. When ordering is not important, you use combination. So what that means is, if I remove this particular phrase or sentence, and in addition, I confirm that, you know, all of these expenses are considered to be the same because the family has more than sufficient money. Okay, then, you know, you have to think, okay, should we use combination instead of permutation? Okay. Now, the other one that is also important is here. The first part is not important. Okay. For 2017 to 2018, the family picked out 20 destinations of interest. So what this part is saying is we have 20 possible things to choose from, but we only get to choose 5. Okay, but the question now is, can I use the same thing again and again? when I choose these 5, okay? So that becomes the next question that is important. Once I have chosen one thing, can I use it again? Can I choose it again? And in this case, it is the case that you can only go to one destination once a year, which basically means that once you choose a particular vacation spot, you cannot use it again. Okay, which means you cannot use the power function anymore, because the power function, which is 20 to the power of 5, means that for each vacation time slot, you can pick any one of the 20. But in this case, we cannot. Okay, because once you have chosen a particular spot or a particular vacation spot, you cannot use it again in that year. So are there any questions about the analysis of how we choose, how we read the description and use the description to narrow down the choices? Yep, go ahead.
I thought the part you had highlighted made it seem where ordering was important. I didn't really see that in the expenses.
The expenses part is actually important as well, because when you can only go to the same destination once a year, okay? It means that you have to eliminate whatever you have chosen from the pool of possible choices, as opposed to not having this assumption or make it very clear that you can go to the same destination multiple times, any number of times. Then you can go to the same spot 5 times. So you don't eliminate a choice because you have been there already.
Okay.
But this part, basically says, if you go to Hawaii in spring break, it's not considered the same as going to Hawaii in winter. So that means, the ordering is important. Okay, where do you put Hawaii is important. Okay. So are there any questions? The rest is really just about how to answer the question, or what I'm looking for in the answer. Yep.
So, for example, if the family could go to the same destination multiple times, it would still be a permutation.
Nope. If you can go to the same vacation spot multiple times, it is no longer a permutation nor combination kind of thing, because you are not removing a possibility based on an earlier choice. Okay, let's take a look at this part here. Okay, so let's say you have 20 choices for the first vacation time slot, right? Okay. If I place the restriction like the one that I have already placed here, that the family can go to the same destination only once a year, okay? How many choices do I have for the next one? I only got 19 left. Is that making any sense? And after I have chosen the first 2 vacation spots, I only got 18 left. And then for the fourth one, I only got 17 choices. And then for the last one, I only got 16 choices. Is that making any sense?
I still don't understand why that makes it no longer, or why that makes it a permutation versus being able to go to the same place.
Because I explicitly said that you cannot go to the same place more than once a year.
But I'm hypothetically, in order to understand the concept.
Right. Now, if you can go to the same spot, multiple times a year, then what you have chosen earlier does not impact your choices later, right? So that means, for the first vacation time, you have 20 choices, but for your second vacation spot, you also have 20 choices. You're not taking that one destination that you have chosen already, you're not taking it out of the consideration of the second vacation spot or the second vacation time slot. Is that making any sense?
Well, I understand what you're doing. What I don't understand is why you're no longer calling it a permutation.
Because this is not permutation. By definition, this is not permutation. This is really just 20 to the power of 5. This is permutation because this is P25, which is also known as 20 factorial divided by 5 factorial.
Well, then that would mean that,
Oops, take it back. This is 20 minus 5 factorial.
that
There
would
we go.
mean that ordering isn't necessarily the defining characteristic.
Well, ordering is important when you need to think about, is it combination or is it permutation? Is that okay or not?
It's not the defining characteristic.
Okay, so let's make it let's consider one thing that will actually make us
I'm just
use.
wondering if we can get a more complete definition of permutation if it isn't as simple as the ordering being important.
Okay, so the actual mathematical definition of permutation is n choosing r is n factorial divided by n minus r the whole thing factorial. And then in combination, choosing r out of n is n factorial divided by r factorial itself times n minus r factorial. So the only difference between these two is in the case of a combination, you have the extra r factorial as the denominator in the division. Okay? But this is actually important. So I'll give you two scenarios that will make this really clear. Okay? So let's say Tom needs to figure out the cost of 5 vacations of a year. Okay? So when you need to look at the cost, the total cost of the 5 vacations, then becomes really kind of clear that when you take that to your vacation is no longer important. Okay, because we are only considering how much does it cost. Okay, if I use up all 5 vacations, how do I make the most out of these 5 vacations in terms of cost effectiveness? Okay, so in this case, I will give you 3 scenarios. Each one will make use of one of the 3 things. One would make use of the power, one would make use of the permutation, and then one would make use of the combination. Okay, so I'm hoping that this will help clarify when to use which one, because it will basically show the restrictions that we need to use in order to narrow down and say, oh, okay, in this case we have to use this. Okay, so we have scenario 1. In scenario 1, we basically say cost of vacation does not depend on time of year. Okay? So we are making this gross assumption here to basically say, okay, if you want to go to Hawaii any day of the year, it is going to be the same cost. Okay? Going to Hawaii in the spring, going to Hawaii in the summer, going to Hawaii in the winter will basically cost exactly the same. So that's the first assumption, which basically say that going in spring, going in summer, and going in winter will be the same. They're considered basically the same as far as the cost is concerned. We're only concerned about the cost in this case, because Tom is only going to figure out the cost of the vacations, not so much the experience of the vacations. So number 2 restriction is whether we can go to the same vacation spot or not multiple times a year. Okay, so in number 2 we basically say we can go to the same vacation spot or the same destination. Okay, destination any number of times. Okay, up to 5, of course. Okay, because you only got 5 vacation time spots. Okay. So using these 2, we can now narrow down the choices to 20 to the power of 5. Okay? Why? So the number of, I shouldn't use combinations, right? The number of ways to arrange vacations is now 20 to the power of 5, given that we have 20 destinations as possible choices, and then we only got 5 times in a year to take the vacations. And the duration, let's assume the duration is the same. Okay. Is that making any sense at this point? Why these 2 restrictions will basically narrow it down to 20 to the power of 5. Okay. Or is it?
Is it considered a permutation or combination or neither?
It is neither in this case. Okay, but is it, okay. I'm suspecting it really is not 20 to the power of 5 because some of these are exactly the same. So if you take, let's just take two destinations into consideration. If the first two are going to Tahoe and the next three are going to Hawaii, versus the first three is going to Hawaii and the last two is going to Tahoe, the cost would be exactly the same. So this is not exactly 20 to the power of 5. In order to use 20 to the power of 5, you have to.
Well,
we cannot say this part makes it not work. Basically, not.
20 to the power of 5 also assumes that the order is important.
Mm-hmm. Because the cost would be the same. We are looking at the different costs. So with scenario 1, I'm going to change this here. Sorry about this. We have to say up to once per year. There we go. Okay, now it makes a lot more sense. Okay, so Tom only needs to consider the cost. And so in this case, as far as the cost is concerned, okay, let's use concrete examples. Okay, so the concrete example is Hawaii, Tahoe, Disneyland. Help me pick 2 more vacation spots. Alaska. 1 more. Florida. Okay, there we go. Okay, so when the cost, as far as the cost is concerned, whether you arrange the 5 vacation spots or the 5 destinations this way, or whether you arrange it this way. Okay, look at these 2 ways of arranging the actual timing of the destinations. Would that make any difference to the cost of the vacations as a total? It would not, because of assumption number 1, the cost does not depend on the time of year. Okay, so as far as the total cost is concerned, these 2 ways of arranging the destinations would be considered identical. Is that okay? And how many, once I have chosen the 5 destinations, Hawaii, Tahoe, Disneyland, Alaska, and Florida, how many ways can I change the ordering, even though it doesn't change the total? It will be the permutation of choosing 5 out of 5, which means we have how many ways of arranging these 5 things?
125.
Not 25.
125. Is it 125?
120. No, not 125. Okay, so let's say, okay, I'll give you one more example so that we can actually look at this. Okay, so we'll go to Disneyland first, Tahoe next, and then the other 3 as the last. Okay, so you can see what I'm doing here. I'm just staying with exactly the same 5 destinations, just reordering these things. How many ways can I reorder these things within just exactly the same 5 possible choices?
It's 120.
It is 5 times 4 times 3 times 2 times 1, which is 120. Okay, so the key here is given 5 destinations, there are 5 factorial ways to arrange the ordering of these 5 destinations. Is that okay? But this 5 factorial, you can see this 5 factorial as the permutation of choosing 5 out of 5 items. Is that okay? But since, but would any one of these 120 ways of arranging the 5 destinations make any difference as far as the total cost of the vacations are concerned? Not under the assumption that we made, right? So that's why, even though you do have, 20, the total number of ways to arrange the vacations even with the restriction of number 2, where you can only go to one destination up to once per year, the actual number of ways of arranging those things is actually 20, the permutation of choosing 5 out of 20. But of those choices, you will have 120 duplicates as far as the cost is concerned. And that's why we have, okay, so that's why, okay, the total number of ways to arrange 5 destinations, 5 destinations, non-repeating, when choosing out of 20 possible choices is always P25, okay, because it's always a permutation. However, out of these ways of arranging destinations, 120 120. Okay, I'm just trying to figure out how to phrase it. I know what is in my mind already. I just need to know how to phrase it. Okay, this is not the best way to express it, but it's kind of going in the direction that I want to go. Out of P25, okay, out of this many choices, if you enumerate all of these, okay, you can group 120 into one single one because they share the same cost, because they involve exactly the same 5 destinations. Is that okay? Yep.
So would you divide the permutation as well?
Yep. Okay. And that's why, as far as the cost is concerned, okay, we only have to consider P25 divided by P55, because these are all quote-unquote duplicates as far as the cost is concerned. They are identical. Okay? So if I was Tom, okay, I would just look at one way of arranging the 5 different destinations instead of considering all 120. Because that would just be a waste of time, because they're all gonna add up to exactly the same cost. Yep.
So you're saying there's groups of 120s that are dupes?
Right.
Okay.
Yep. Is that making any sense? Okay. So this is when we use combination. When we basically say that the cost does not matter depending on what time of the year, and we're only concerned about the cost. Okay, because when you add up, how you add up, because addition itself is commutative. That is the reason, okay, in terms of math reasons. Okay.
And we could represent Tom's choices with a set rather than a tuple.
That's exactly right as well, because in a set, ordering is not important. Okay, so let's look at scenario 2. So in scenario 2, the cost of vacation does depends on time of year. So in this case, I look at these choices, okay? I can look at these 3 ways out of 120, okay? Let me make it very clear. This is only 3 as examples out of 120 possible ways to arrange these 5 destinations. But when you look at the cost of each way, it's not going to be the same anymore, okay? Because, I'm assuming, because it's cold in most places in the winter, so a trip to Hawaii will cost more because more people want to go to Hawaii in the winter. Okay, and going to Alaska in the winter may not be as expensive because a lot of places probably you cannot even go there because of extreme cold in Alaska. Is that making any sense? So that's why these 3 ways of arranging these particular 5 vacation spots or destinations will give you different cost as a total. Is that okay? So as a result, if I'm Tom, if the cost of vacation depends on the time of year, I just end up with a lot more choices to choose from. So in this case, it is just the P25 because we don't have duplicates anymore. Okay. So let's look at scenario 3. So in scenario 3, the cost of vacation does depend on time of year. That's one thing. And then on top of that, we can go to the same destination, any number of times as long as it is less than or equal to 5. So in this case, we are not taking a choice out just because we went there already earlier in the year. Is that okay? So now what are we considering? We got 20 choices to choose from for the first vacation time. We get another 20 to choose from, not 19 anymore. Because I can go to Hawaii 5 times a year. So you get 20 times itself up to, exactly 5 times, which is 20 to the power of 5. Yep.
That one's like scenario 2.
Oh, this is actually scenario 3.
It's like scenario 2 though, where each one's different.
Correct.
Okay.
Because if the cost of vacation does not depend on time of year, then we have a much more complicated problem. Because now you can say, okay, I can go to Hawaii 4 times at the beginning of the year, once at the and then the last one is going to Tahoe. That's going to be considered the same as going to Hawaii for the first 3, and then Tahoe, and then the last one is Hawaii again. So now we have to look at those 5 and go like, oh, they are really the same. And then you have 3 vacations going to Hawaii, and 2 other ones going to Tahoe. And then you have to figure out how you can interleave those 2 spots. Yep.
So I guess what I'm wondering about scenario 3 here is, do we just not have any notation for it? We don't call it a permutation and we don't call it a combination? Is that just because you can just...
Because each choice is completely independent to what you have done before.
But the ordering is still important.
Hmm?
But the ordering is still important.
The ordering is still important because they do not give you the same cost.
Now,
And it is still important, yes.
Now, do they... I'm wondering if maybe they don't have any particular notation for this just because you can do 20 to the power of 20 to the power of 20.
There's no particular notation. It really is just multiplication because the choices are completely independent.
Huh.
Now, scenario 4, if I remove, if I change restriction number 1 and say the cost of vacation does not depend on time of year, then I have just created a kind of more complicated problem, because now I have to consider. Okay. Do you guys want to go there or not? Because I'm not going to ask that question in the exam.
I'm
Yeah.
curious, but if it takes time away from the other.
Well, okay, maybe I'll just list it here, okay, but not to actually talk about the solution. But the scenario 4 is basically saying the cost of vacation does not depend on time of year. Does not, depends not, okay, that sounds like Yoda talk. Okay, does not, okay, does not depend on, okay, there we go. Okay, so the cost of vacation does not depend on the time of year. Okay, and on top of that, we say that we can go to the same destination any number of times up to 5. Now we have a more complicated problem, because now you can say, okay, so in this case it's a bit more complicated. It's not just combination and permutation, because now we can say, oh, we can go to Hawaii 5 times. Okay, that's an easy one. But every single destination, you have 20 of these cases, right? Okay, so you have 20 times 1, okay, that's 1 category. What about going to Hawaii and Alaska? Well, how many do we have in this case? Because we can do it like this, right? And that. Is that making any sense? And then you say, well, I can go to Hawaii 3 times and Alaska twice. But then you can say, oh, we can do it like this too. And then you can interleave, right? And then you can also do it like this, right? Now, there's a particular way to look at this too. Because in this particular case, because it's kind of the same thing as the head and the tail issue, right? So the question is, how many ways can you arrange 3 trips to Hawaii and 2 trips to Alaska as a sequence? What do you think?
Well, aren't we basically looking at how many ways we can arrange 5 different things?
Well, this one is easier because it's either Hawaii or Alaska, which means once you lock down the 2 choices for Alaska, you automatically lock down the 3 choices for Hawaii. So it becomes a combination issue. So it becomes 5 choose 2 or 5 choose 3 because they give you the same answer. Okay. So this one is not too bad, but when you involve 3 possible destinations, let me just kind of chop this up first. So I would just say ... here. Okay, but the point is, we have this many ways to arrange 3 trips to Hawaii and 2 trips to Alaska. Okay. Well, let's do some checking here because it seems like.
Wouldn't it be in 20 to the 10?
Nope. Okay, so there's one here, okay? So you can look at this as, C5, 5, okay? So now the question is C5, 5, 1? If I want to choose 5 things out of 5 things where the ordering is not important, is there only one way to do it? The answer is yes, okay? Because we need everything. But let's double check with the definition of combination. The definition of combination is, in this case, is 5 factorial divided by the product of 5 factorial times 0 factorial. Well, that is exactly 1. So it works out, okay? In this case, it is supposed to be C5, 1. It is 5 factorial divided by 4 factorial times 1 factorial. Is that 5? It is, okay. And in this case, it is 2 or 3 is the same, okay. So that turns out to be what number? 5 factorial divided by 3 factorial times 2 factorial. 3 factorial is 6, 2 factorial is 2, so we actually end up with 10, I think. Okay, let's double check. 5 times 4 is 20, 20 times 6 is 120, so 5 factorial is 120, but there's a division here. 3 factorial is 6 because it's 3 times 2 times 1. 2 factorial is just 2, so we have 12 as the denominator. 120 divided by 12 is 10. Yep.
What's interesting is 5 choose 3 is 10 too. So
Exactly. Yep. Because once you lock down the Alaska time slots, you lock down the other ones, which are Hawaii. But you can also say the same thing. Once you lock down the Hawaii time slots, you lock down the Alaska time slots because they are the other ones. So that's why they're equivalent. Now, these are the easy ones, okay? Because the next one is, this one, which is basically the same thing as this one here. There are exactly 5 ways to do it. But when we get to 3 destinations, it gets nasty because, okay, if you consider Hawaii and Disneyland, okay, and you say, okay, we go to Disneyland 3 times, okay, now it gets a little bit more complicated because once you lock down the Disneyland destinations, you still have permutations of going to Hawaii versus going to Alaska, so it gets a little bit more nasty.
We're getting into password territory. So we're getting into password territory.
In what way?
In the combinations of the possibilities for
Unique choices or
Yes.
unique ways to have a sequence
Yeah.
based on these restrictions, yes. So that's why,
where you can repeat.
you can repeat, in this case, you can repeat,
And the ordering is important. That's a password.
Yep. So that's why in scenario 4, it's actually a lot more difficult to deal with.
And much more interesting.
It is more interesting. Is that okay? And the difference between scenario 3 and scenario 4 is very seemingly minor. In scenario 3, we are basically saying the cost of vacation does depend on the time of year, and in scenario 4, we say the cost of vacation does not depend on time of year, which basically makes these considered the same cost, and then these considered exactly the same cost, and there are 10 of these that have exactly the same cost, total cost. Okay? But in the other one, they're not the same. Okay, whether you go to Alaska, in the winter, or whether you go to Alaska in the fall versus going to Alaska in the spring or in the summer or in the spring, they're all different. Is that okay? So are we so far okay with the topic of permutations versus combination? Okay. All right, so moving on to discrete probability distribution. This is when we actually talk about, when we talk about the binomial theorem, that's when we introduce proof by induction. Okay, so can someone remind me of the 2 steps of proof by induction?
You prove it for one case, and then you prove it for the case after that, like the +1 case.
Okay, well that's a very kind of a good summary, but to be exact, okay, when you're dealing with proof by induction, you need to have two steps. Okay, it's 2 steps. Okay, proof by induction involves 2 steps. Step 1 is what we call a base case. So the base case usually is a very simple one. You basically look at the range of values where the theorem is supposed to apply to. Okay, so use one extreme of the set of values where the theorem applies. Okay. Okay. So just to be very clear, okay, when you prove by induction, the type of problem that you can prove by induction is limited to the cases where proof by induction is basically saying it is true that for all x in a particular set, okay, some kind of predicate x is true. Okay, so let me just put double quotes around these so that we know exactly what we mean. Okay, this is not an empty set. This is usually some kind of numbers. Okay, set of whole numbers. Okay, or I should say integers. Integers, and make it a subset. Okay. So it usually has a range, and it has one limit on one side. If it doesn't have limit on one side, you can still use proof by induction, but then you need 2 proof by induction, or 2 induction steps. We don't deal with those in this class, so everything that we do, this particular subset is usually just the natural numbers. Okay, 0, 1, 2, 3, 4, and so on. Okay, the nice thing about natural numbers is there's one extreme end where you can say, hey, that's the smallest number we can deal with.
0.
Which is 0, exactly. If I make this actually the set of all integers, then you have a bigger problem, because what is the smallest integer value? We don't know, okay? Because it's not negative infinity, because infinity is not a number.
I would be facetious.
Yeah, but there's no such thing as the smallest integer. So if I say, it's all, for all x is an integer, the p of x has to be true, you can still use proof by induction, but then your induction step will involve 2 processes, because you have to prove by the induction step has to go forward and also backwards. Okay, but with natural numbers, it's easy, because you find the smallest number to begin with, which is a 0. Is that okay? All right. So that's the base case, okay? So in this case, usually we choose the smallest value where the theorem applies. Okay, so in the case of all natural numbers, we choose 0 as the base case because it's the smallest number. It is at one single extreme. So in the step 2 of an proof by induction is called the induction step. Okay, so the induction step is a little bit tricky because it's very easy to kind of not fully understand what the induction step is and use it incorrectly. Okay, so the induction step assumes, okay, it involves the assumption, assume P of X, P of K is true. Okay, and remember what P is? P is just a predicate, or if you want to look at it, if you don't want to use the term predicate, it is some gigantic expression that is true for value X. Is that okay? So in this case, we make the assumption that P of K is already true. Okay, there's no solid proof that P of K is true for some K that is in the set that we are dealing with. Prove that P of K plus 1 is also true. So if you can make this link, if you can actually do this proof by assuming P of K is true, and you can actually prove that P of K plus 1 is true as a result, then you're done with proof by induction. Okay? Now, we haven't used this in this class, and I really doubt that we actually need to use it in this class, but you can also work backwards. Okay? So the alternative induction step is like this. You can also use this in the opposite direction. If the set of values you're dealing with has a known and definite upper limit, and then has an infinite value or infinite number of elements on the negative side. In other words, if this particular subset involves all non-positive integers, then you probably will have to do it this way. You establish that 0 or -1 is the base case, and then you say, okay, assume P of K is true, then you want to prove that P of K minus 1 is also true, because that's where you need to do all the stepping. Is that okay? Or not? Okay, just imagine, in your mind, imagine that you are, I dropped you off, on top of some kind of quicksand. Okay, so you don't want to stand on quicksand by yourself. Okay, so I give you, I give you one tile. Okay, that is quicksand proof. You can actually stand on it. Okay, or one spot, that you can actually stand on. Is that okay? That's your base case. So now I give you another mechanism and say that, okay, so you can move, you basically have 2 steps, okay, 2 tiles. So you can move the other tile in front of you and walk forward, and not to sink into quicksand, right? Okay, so given if you have the mechanism to walk forward by 1 step, and where I want you to go is like 20 miles away, can you get there in theory? Assume that you don't need food, drink, water and stuff like that. In theory, you can't get there because you just go step by step, right? Because I give you the mechanism, I give you a safe spot to land, okay? And then I give you a mechanism to walk, 1 step in the direction that you need to go. Well, then you walk 1 step, you pull the other tile forward, you walk another step, you pull the other tile forward, and you keep going. So no matter how far the distance is, but as long as it is in the direction where your magical steps can go forward, you can always reach it. And that's the whole idea of proof by induction. But in order for you not to sink into quicksand, you need 2 things. One is a safe landing spot, okay? And the second one is the mechanism to go forward. But to go forward, you can just assume that, okay, I'm already on solid ground, or I'm already on a spot that is not sinking. Don't ask me how I end up here, okay? But as long as I have a mechanism to establish the next safe spot to walk forward, then I can walk indefinitely, go to whatever direction, go to whatever destination is in that particular direction. So that's the whole idea of proof by induction. Is that making any sense? Sort of? Okay. All right. We talked about Pascal's identity, which is basically looking at Pascal's triangle and say, well, why does it work? How does it work? Can we prove that it always works? And the answer is yes. Okay, we did prove that. The binomial theorem is another theorem. Okay, I'm just going to go there for a little bit. The binomial theorem is this one here. Okay, it's basically just saying if you have 1 plus x or x plus y, it doesn't really matter, but you have a sum of two things to the power of n, then I can express how these I can express the individual terms using n choose I as the coefficient, and then in this particular case it's just x to the power of I, but if you have x plus y, then it will be a power of x times a power of y, a product of those two. Is that okay or not? Are there any questions about the binomial theorem? What is it really saying? The reason why we don't have the other power is because 1 to the power of everything is 1 itself. So that 1 to the power of something is actually absorbed here and just not being displayed. Is that okay?
Could you give an example of one of the calculations?
Absolutely. Actually, I think, let me see if the next slide already talks about that. Because the next one talks about binomial distribution, and I'm pretty sure we talked about this one because I talked about coin tosses. Okay, so in this case, okay, so let's take a look at this one. Okay. All right, so in the mathematical notation, we have x plus y, and then the whole thing to the power of n. Okay. So now the question is, how do I express the x plus y as a whole thing to the power of n, and what are the individual terms of this multiplication? That's what I'm interested in. Is that okay? So we know certain things for sure, okay, because we already know that there is a x to the power of n somewhere, okay, and there's only one of these, okay, there's only one x to the power of n. Is that okay? Plus something times x to the power of n minus 1 times y. Is that okay? Because when you have, okay, let's say n is 4, okay, just for argument's sake, let's say n is 4. We get x plus y, x plus y, x plus y, x plus y. I'm just spelling out x plus y to the power of 4, okay? So how do you figure out the actual individual terms as a product of a power of x times a power of y? Using the distributive law of algebra, so what do? So you can say, well, we can choose x from the first parentheses, choose x from the second one, choose x from the third one, choose x from the fourth one. That will add up to just one single x to the power of 4. So at the end, we have x to the power of 4. Okay, the next term I want to figure out is, okay, so how many x to the power of 3 times y do I have? I know I have at least one, right? Because you can choose x, choose x, and then choose y. That will give you x to the power of 3 times y. But now the question is, how many of those do I have? So I want to fill in this space here. What do you think? I'll give you a hint. It has to do with choosing, okay?
4 choose 3 or
4 choose 3 or 4 choose 1, they give you exactly the same number, okay? The next one is x2, y2. Okay, x to the power of 2 times y to the power of 2. How many ways can I choose 2x and 2y's? 2x and 2y. How many ways can how many combinations do I get? That's a big clue right there. It's 4 out of 4 spots. I need 2 of those spots being x. Okay. The next one is x to the power of 1, y to the power of 3. How many combinations do we get? When you look at this pattern, you can kind of, you know how what the next one should be. 4 choose 3, which is the same thing as 4 choose 1, okay, because the combinations, you know, this number can, in this case, can be, as long as they add up to 4, they are considered the same. Okay, what is the last one? Y to the power of 4. How many ways can I make a y to the power of 4 when there's only one, but technically it is 4 choose 4. Okay? How about the first one? Okay, everybody has a choose something. Okay, if I want to make it here and follow this pattern, what is it going to be? 4 choose. I used 4 choose 1 already. 4 choose 0. Okay. Here we go. Does that relate to the binomial theorem? It is. Because in the binomial theorem, y is 1. Okay? So 1 to the power of whatever is just that 1. So that's why, you know, we don't see 1 to the power of something, but it really does relate to that. Okay? So given this picture here, okay, let me just summarize this as a summation. Okay, so we'll say x plus y to the power of n is the summation of I being an index going from what to n? What do you think? If you just look at the picture on the right-hand side, what is the first number I should use for the index I? I already know the other side is n. What should I use as a starting point? Should I use 1 or should I use 0? 0. Okay. And choose I, right? Because for each term, it is determined by the indexing variable itself. How many x are we talking about? How many y are we talking about using that particular pattern? Or what is the power of x and power of y involved here? N minus I for x is the power, and then just I for y. Is that okay? Do you see how this is a generalizing equation to capture what we have worked out here? Okay? But isn't that really just the binomial theorem? This equality is not guaranteed. We have to prove it. But using the same technique, the very same technique that we prove in the binomial theorem, when we use a constant one as y, we can prove this as well. We can prove this equality. Okay? Is that okay? All right. But why is this important? Remember the 3 levels of questions. This is the kind of low-level detail stuff. This is the how. What is it? Yep.
Well, in this case, it allows us to express the same thing in 2 different ways.
Okay. But why is that important? Okay. So we want to get to the what and the how and the why.
You could tell what some of those coefficients are without having to completely
Carry out the
do the
multiplication.
whole equation. You can just pick one of them.
Yep, exactly. And that is useful because
Saves time.
it saves time, but in this class, we are not, remember, this is not a calculus class. So this is in the context of probability. So why is this important in probability? So let's check out the this particular note here, binomial distribution, okay? So in binomial distribution, we are talking about something that can either be one or the other state, okay? Like a coin toss, okay? Okay, so let's forget about this for now, okay? So let's forget about the binomial theorem for the time being. And just think about a coin toss problem, okay? So let's just say that we have a loaded coin, okay? I have a loaded coin, it lands on heads like 60% of the time, it lands on tail 40% of the time. Is that okay? So we have a coin, and the head has a chance of 0.6, and the tail has a chance of 0.4. Do you notice what, no matter how you load a coin, the chances of landing on the head plus the chances of landing on the tail is always 1. Okay, very good. Okay, so that means I can express one as, okay, I pick this one as P, okay? Then how can I express the other one?
1 minus P.
1 minus P, very good. Okay, so we can express this as 1 minus P, and let's just call it Q, okay? Is that okay? So I'm going from actual, constants to variables, and then we express, the two variables, but one is really, dependent on the other one. So we can say one is P, the other one is actually 1 minus P, but for notation purposes, we got a Q. Is that okay? All right? Okay. So let's say we toss the coin exactly n times. Okay? We toss the coin exactly n times, and I'm interested in the probability of having a certain number of heads and a certain number of tails, the rest being tails. Is that okay? All right? So we are toss a loaded coin n times. Okay? And I'm interested in, okay, what are the chances that we end up with, k of these, tosses being heads and the rest being tails? That's what I'm interested in. Is that okay? All right. So I asked the question. Okay, the question is, what are the chances that k out of n tosses are heads? That's the question. So now we're talking about several things that seemingly are not related, okay? Because we started off talking about binomials, right? 1 plus x to the power something, okay? And then we say, okay, instead of using 1 plus x, we can also say x plus y, because the general format works too. Not a problem. Now we talk about something that is completely different from that whole discussion. It's like, okay, here's a loaded coin, I'm going to toss it n times, and I want to find out, okay, what are the chances that, out of these n tosses, k of those are heads. And we know the chances of a head landing is P. So how do you figure that probability out?
So this is as if we did not already know the 0.6 and the 0.4.
Well, okay, can I erase the right-hand side? Is that okay? All right, so I'm going to erase the right-hand side. Okay. Out of the first toss, this is the total of all the possibilities, right? We get P, which is 0.6 in the example of chances landing on the head, and Q, which is really just 1 minus P, which is 0.4 of chances landing on the tail. It adds up to 1, okay? No big deal. If I toss it twice, then I can do something like this to represent 2 tosses of a loaded coin, where P is the chances of landing on the head, and Q being the chances of landing on the tail. Is that okay? Because this is really kind of the crux of the whole thing.
So is this the chances of it landing on the head or tail once?
No. This 1, now this is always 1 because P plus Q is always 1. It has to be a 1 because this is accounting for all the different possibilities. But in this particular case, let's just look at this one single case here, okay? What is the, if you expand out all the terms, what do you get? Come on, you guys can do this really quick, right?
P squared plus 2.
Exactly, okay, it's P squared plus 2PQ plus Q squared, okay? But what are these things representing? What is P squared representing?
Heads.
The chances of having exactly 2 heads. Q squared, the chances of it having exactly 2 tails. What about 2PQ? What is that representing?
The chances of it being one of each.
Exactly. Do we care about head first or tail first?
Doesn't look like it.
Doesn't look like it. Very good. Okay. So this is basically the chances of having exactly 2 heads. Okay. This is the chances of having 2 tails. And this is the one that is just saying, we have 1 head and 1 tail, but the ordering is not important. Is that okay? Now we want to generalize this and go like, oh, but I don't want to just lock down 2 tosses. I want to make it general to n. And I'm not interested in just 2 heads or 2 tails. I want to know, what are the chances that k out of n, and k can be 0 all the way up to n. Okay, so but we use a k to represent k out of n tosses are heads. Do you see how this may have something to do with this? Okay, so let's answer this question then. So if I toss a loaded coin, the chances of landing on the head is p, the chances of landing on the tail is q, okay? And I'm only interested in, okay, what are the chances that I will have k out of n tosses being heads? Okay, what do you think? So the first thing we say, p plus q to the power of n, which represents the number of tosses, right? Is the summation. I goes from 0 to n. Okay, I'm just repeating that whole thing, except I'm not using x plus y, I'm using p plus q. So this is all basically the same thing. X n minus I, y, I here. Okay. Let me just draw a line here because these things are different, separate. Okay.
Can we induce a trinomial for him?
No. This is still binomial because we only got 2 things inside the whole thing. Okay. So what are the chances? Come on, tell me. So we are looking for, oh, not x, y, sorry. Here, I kept using the same one here. It's p and q, right? P, q. There we go. So we are looking for the case where p is k, or the power of p is k, because that represents exactly k times being heads. Is that okay?
What was that? I missed that.
Okay, so we are looking for the term where p, the power that applies to p is k, because that's what we're looking for. We are looking for the chances of k out of n tosses are heads. And the chances of 1 in each toss that you get a head out of that toss is p, so we want this to be p to the power of k, right? Okay, so if we're interested in p to the power of k, that automatically makes the q what? Well, k, what is the relationship between k and n? Well, k and this number here. They have to add up to. They have to add up to. If you look at these two, they add up to n. They have to add up to n. So q in this case is n minus k.
Yeah.
So this is the probability, but this is the probability of only 1 sequence of toss. Because there are many ways of having that particular combination. Are we doing okay so far? Okay, let's plug some real numbers into here. Okay, so let's say that k is n is 20 and k is 6. Okay, so we're asking the exact probability of out of 20 tosses that we end up with exactly 6 heads. Okay. Well, let's see. We can have head, whole bunch of heads. How many of those? 6. And then the rest are tails. So there are 14 tails, right? This is one way to end up with 6 heads and 14 tails. Tell me another way to do this that would end up with 6 heads and 14 tails. We can have 1 single head, okay, a whole bunch of tails, and then 5 heads. 5 heads, 1 here, and then 16 tails. 14, sorry. Is that okay? All right. So that means, we have a lot of ways to end up with exactly 6 heads out of 20 tails. How many ways do we have? This is where the binomial theorem kicks in and go like, oh, okay, so there's the answer. What do you think? When Q is n minus k, you plug this back into this equation, right? This is I, this is I2. So there within this expression, there are exactly n choose n minus k of these items. I'm just plucking one term out of this summation, which is the one that we are interested in. Is that okay? Or not? We're okay? All right. So this term here, which is really just one term out of the entire summation, is representing the chances of k heads n minus k tails. We got our answer. This is the answer to that question. Is that okay?
So does your summation start at k equals 0?
I start from 0.
Okay. So then that's not a summation, the answer?
This is one term of the summation, but it answers our specific question, which is the chances of out of n tosses with k heads. And P is not necessarily the same as Q because it's loaded.
I was confused because you switched to I, but then you didn't change it in the summation.
In the summation? Yeah, I did. The summation has I, but in this one I'm pulling one term out of it because this is the only term that I'm interested in. Okay? So I'm just looking at one single term, which is the one that I'm interested in, because that answers the question of what are the chances that we have k out of n tosses being heads. Is that okay or not? Good. Okay, all right. But this is important because, you know, I'm running out of time. I'm going to go to the sample questions in the test. You might want to look over those, you know, just to see if you can answer those questions. But for the most part, you know, other than recursion and the master theorem, I have covered, you know, the scope of the test for exam number 2. So it is actually time to look at the practice exam, which is the spring 2016 exam 2. It's a PDF, but this is exactly the exam from last semester. And one of the questions, okay, which is a coin toss question. So question number 3 is directly related to what we have just talked about. Assume a coin is not fair, okay? It is loaded. It is fair and not loaded. This means the probability of a head or a tail after a toss is considered the same, which is 0.5. Does that make sense? P and Q are both 0.5 in this case because it's a fair coin. So in this case, at a casino, okay, the casino claims the coin is fair. Okay, as they always do. But an observer, you observe the counts of results of a lot of sequences of tosses. Okay, so you observe, you know, you spend a whole day there and you observe. And each one is a sequence of 4 tosses. The observation or the observation is of all the counting. There's a total of 79 sequences ending up with 1 head and 3 tails, and a total of 146 sequences ending with 2 tails and 2 heads in any particular order. Okay? What about the other one? I'm missing one, I'm missing actually, let's see, 0, I got 5 to begin with. I'm missing 3 combinations of heads and tails. Which 3 am I missing here that I did not report the frequency count?
1.
Okay, so the way,
3 heads.
exactly. So the way you do this is, okay, this is the number of heads and the number of tails. I'm making sequences of 4 observations. Okay, so you can in 4 observations of coin tosses, the possibilities are you get 0 head 4 tails, 1 head 3 tails, 2 head 2 tails, 3 head 1 tail, and 4 head 0 tail. Okay, but because I lost some of my notes, I can only remember the frequencies of 1 head 3 tail. Okay, so I have the frequency count of this one, which is 79, and I have the frequency count of the other one, which is 2 head 2 tail, in this particular one, and it is 145. But these have their own frequency counts too. I just do not know what they are. I forgot to take the frequency. I forgot to count for those particular frequencies. Is that okay? Does everybody understand the given part of this question? Okay, so given that the observation is, I have 79 observations of 1 head 3 tails as a sequence of 4 coin tosses. I have 145 sequences of observations of 2 head 2 tails in any particular order. We want to answer the questions. Okay, so we have 3 parts to this question. The first part is, how would you check whether the coin is loaded or not? Just based on these 2 numbers, the 79 and 145, how can you determine whether the coin is loaded or not? Okay, and if you read this part, you may use any formula without exact numerical values, and use conditions involving these formulae to indicate how you would make decisions or how you make your conclusions. In other words, tell me what you're comparing to in order to come to the conclusion whether the coin is fair or not. That's what I'm asking. Okay? And then the second part, the part B, is if you figure out how to check whether the coin is loaded or not, indicate how you figure out how the coin is loaded. So let's say that you say, oh, I think the coin is loaded, okay? Or this is how I would figure out whether the coin is loaded or not. But assuming the coin is actually loaded, how is it loaded? In other words, tell me what is P and what is Q. Based on the observation, tell me what is P and what is Q. And then part C is assuming the observation is representative of the nature of the coin. In other words, this is actually how the coin is behaving normally. Present equations that can be used to solve the actual probability of a head versus a tail outcome after a single toss, which is basically what is P and what is Q. All right. So are there any questions about the question itself, what I'm asking and what you are given with? Okay, you went to a casino, you observe, coin tosses. Each sequence of a coin toss involves 4 tosses, and you're counting. You're basically just standing on the side counting and say that, okay, I observed out of all the observations that I've done, 79 of these observations end up with a sequence of 1 head and 3 tails in any particular order, and 145 observations of 2 heads and 2 tails. These are unreported. I don't know how many sequences end up with all 4 tails, how many sequences end up with 3 heads and 1 tail, or how many sequences end up with exactly 4 heads and no tails. Those are unreported. Only these 2 are reported. So now only using those 2 numbers, how do you figure out whether you think the coin is loaded or not? If you think it is loaded, how it is loaded? That's the question. So first of all, do we have all the information that we need to get this computation going? We don't even know the total number of observations. In other words, without knowing these unknowns, we don't even know how many sequences of 4 tosses that we have actually observed.
You know how they relate to each other, though.
Yes,
And
you
can
know
check to
how.
see how the 2, if they were unweighted,
Yep.
if they were fair, you can check to see what the ratio between those 2 numbers would be.
Yep, exactly. That is exactly how we are going to solve this problem. And we have maybe 2 minutes left. I'm going to use up 2 more minutes. Okay. So we know this one is representing 4. You can 4, 1, 4, 3. Doesn't really matter because they are the same. So you can say 4, 1 times Okay, p to the power of, this is 1 for heads and 3 for tails. Okay, so this is representing the ratio of this observation. And then the other one is 4 to p squared q squared. And this one is representing this number here. So when you look at these two numbers and the number of observations, which is 79 versus 145, this ratio should be the same as that ratio. Is that okay? So even though we really don't know the total number of observations here, we have enough information already to come to that conclusion. To figure out how to solve this problem. Is that okay?
Do you want to expect the ratio to always be exactly the same though? Like would there be some kind of like standard of deviation that we could use, or was that like overthinking it?
Okay, so if you start to change p and q, we know how p and q are supposed to relate. Mm-hmm. Q is 1 minus p.
But in the observable ones, you would expect there would be differences in what you would observe.
This is the actual observation, and in part 3, I'm saying that this is actually representative of the behavior of the coin itself.
Yeah.
So it's not like, oh, this is just really one off, really odd chance that it would end up with this combination. Mm-hmm. So from 79 to 145 as a ratio, we know that this ratio should match the ratio of these two numbers. Well, we know what is 4 choose 1. It is 4 times 4 choose 1 is 4 divided by 1 factorial times 3 factorial, which is basically just 4. And we know the ratio of this one as well. 4 choose 2 is 4 divided by 2 factorial times 2 factorial. So we have 12 divided by 4, which is 3. Okay, so we know the expected ratio. If the coin is not loaded, then p to the power of 1 times q to the power of 3 is exactly the same as p to the power of 2 times q to the power of 2, because they're all 0.5. Okay, so we know the chances of the coin not loaded but ending up with this particular ratio. So now the next question is, does that look reasonable to you? I mean, is that a reasonable number? We're running out of time today, so I will continue this on next Monday. Yep.
When is the exam?
The exam is scheduled 1 week from today, so it depends on how far we can get on Monday. I might consider postponing that to the Monday on the Thanksgiving week. But I'm hoping that we can get it to next Wednesday.
I feel like a lot of people are conflict too. They might not hear that we have a second.
Well, it's all recorded.
Professor, you're saying that what ratios were supposed to match? I didn't catch that.
They're supposed to match because this is what you observe. This is theoretical what they should be.
Okay.
So if what you're observing is representative of the actual behavior of the coin, in other words, it's not really just some really odd sequence that won't happen